Hello, good morning. I hope you're doing well today.
Good morning, Professor.
Just a couple of announcements. Our final will be, according to the university's final schedule, will be on Friday during the finals week. So next week will be our last week of class. In the final weeks will be December 6th to the 10th. So our class will have finals on the 10th, Friday. Well, since it's an online exam, it doesn't have to happen at a particular 2-hour window, so it will be open for 24 hours on the 10th, and you can choose any 2-hour period that you are available to do the exam. And the practice exam is posted on Canvas, so make sure that you have some time to do it before you look at the solution, which I will post later this week. And other than that, the content coverage will be everything after, will be heavily focused on everything after the second midterm, but it is cumulative in the sense, yes, you still need to know how to do the Newton's second law, you still need to know how to apply conservation of energy, but you can spend majority of your time to prepare for the content after the second midterm. So that's where we started rotational motion, rotational kinematics, rotational dynamics. We talked about angular momentum and conservation of angular momentum. And we did static equilibrium. And then we talked about universal gravitation. Right now, simple harmonic oscillation, and then fluids. So these will be covered on the final. If you have time, I encourage to try to do more practice exams on your practice homework problems on your own. You can find a lot of practice at all sorts of resources online. You can look at your textbook. So at the end of the chapters, there's always a lot of practice problems. So that would be a good way to make sure that you know how to apply the content from problem to problem. All right, so that's my announcements. Do you have any questions?
So then, Professor, to be clear, we don't do we have class the week of December 10th?
We do not. The week of December 10th is only finals week. We do not have class. So our class will end on December 3rd. So that will be our last day of class.
Oh, okay, thank you. So then do we have office hours that week?
Sure. I will keep this regular office hours. So if you have questions regarding the when you prepare, then you can always come and ask.
Cool, thank you.
Of course. If you any other questions later on you think of, feel free to email me. Okay, let's get back to our simple harmonic oscillation. So at the end of Monday's class, we were talking about how we can still apply conservation of energy to relate the two different moments. Initial moment being, now you can decide whatever your initial point to be, if it's really just oscillating back and forth, right? So it doesn't really matter which one happens first. But initially, if you think initially it's the spring is at a maximum stretch, extension, and finally, if you think of the spring is in the point O, right in the middle, so initially all potential energy and finally all kinetic. So you can use conservation of energy to solve for the maximum speed the object could have. So we did that. So let's apply this on a question that's very similar to that. If we're having two different masses that are identical, but we attach them to two different springs, one is more stiff, one is more floppy. Okay, and think about their initial conditions, right? So you can make the oscillator by either stretch it and let go, or you can simply give it a quick tap and give it initial speed, and then it will start oscillating, right? So both of these would be a way to give it some initial condition. So in this case, you give it a initial speed when it's at the equilibrium point. And then we're asking which one produced the largest amplitude. So it's kind of a reversed order than the one we did before, right? The one we did before, it's at the largest amplitude and then you let go. And it's asking what is the maximum speed. In this case, we have the speed and then we are asking about the amplitude. All right, so I'll go ahead and let you vote on this. You do not need, you can answer this qualitatively, but you can also set up equations to solve it. All right, so let's go for another 10 seconds. All right, I'm gonna go ahead and end this with, we'll take a look at this together. So which one give us a bigger amplitude? We're pretty much split between choice A and B. So amplitude is simply meaning that when you give it quick velocity and let it go, is it going to oscillate back and forth, which one gonna go further out in the end and further out and in? So that's what we mean by amplitude, right? So you have a stiff spring versus a floppy spring. So just intuitively, which one do you think we're gonna be able to go further out?
Floppy spring?
I'm sorry, I couldn't hear.
Oh, sorry, the floppy spring?
Yeah. So in this case, we could fully rely on intuition. There's nothing more to it. The floppy spring will certainly be able to stretch out even further, given the same velocity to begin with, right? Okay, very good. Now let's see, okay, how do we answer this rigorously using physics? In particular, we will use conservation of energy. So here, if they're just sitting here, right? They're just sitting here, and you give it a velocity. So this will be your initial moment. And your final moment will be when the spring is stretched to a maximum. So this would be considered the amplitude. So you're looking at a kinetic energy transformed into potential energy of the spring. So let's take a look at our math. The beginning is all kinetic. I have 1/2 mv squared is my energy, and the v is the velocity you give the spring, okay? So they all have the same velocity to begin with. And final energy is all potential. That's 1/2 Ka squared. A is how much is being stretched. That is also the amplitude we're talking about. K is the spring constant. So if you have a stiff spring versus a floppy spring, Which one has a bigger spring constant?
The stiff spring has a larger spring constant.
Yes. So spring constant tell us how much force it is required to stretch it for this much distance, right? So tell us an idea how hard it is to stretch it. So the stiff will have a bigger K. So you can see that if they all start with the same amount of energy, whichever has a bigger K will have a smaller A, because 1/2 Ka squared is the same value. So the floppy spring with a smaller K will be able to have a bigger amplitude with a bigger A. It's going to be able to extend further. All right.
And
So that,
Professor,
yes.
sorry, if we have time, would it be possible for you to solve this problem using the equation, not from a non-energy perspective, using the equations for like the angular velocity and the what do you call it? Sorry, and the motion equations for the spring?
Oh, yes, absolutely. Okay, so let's take a look. We want to do it that way. Let's first write down the equations of motion. I know I would want a sinusoidal function. So which function will best describe my position with respect to time? So I know at t = 0, my position is at 0. My velocity is at its maximum velocity. So it looks like I would need a sine function. Okay, so x would be amplitude A times sine of omega t, because this satisfies that at t = 0, position is 0. If I take the derivative of this, I get velocity that satisfies negative A omega cosine omega t, which is at t = 0, this is cosine is a 1. So that satisfied. All right. Okay, so what else do I need to consider? Omega, the angular frequency. So we talked about here, the omega is in intrinsic nature of the spring. So in this case is square root of K/m. So what differs between these two kind of cases is K is different. So omega, so if we call the stiff spring has a K1, then the floppy spring has a K2. So you have an omega 1 and omega 2. In this case, they have different omegas. Okay, so this would have been my x A1 sine theta 1, right? And my floppy would have a different equations of motion. So, okay, so what am I comparing right now? Okay, so I know they're giving the same velocity. Okay, we not. And that's the maximum velocity you can have. That's right in the middle. So you can see my maximum velocity is A times omega. Okay, so I know that A1 omega 1 is V0 for the stiff spring. A2 omega 2 is also V0 for the floppy spring. They all are given the same V to begin with. So we want to compare A1 versus A2. And then we can see, let's compare omegas, right? Omega 1 is a stiff spring, has a bigger K. So omega 1 is larger than omega 2 because K1 is larger. So square root of K1 is larger. So you can see if they are all multiplied together to be the same value, we know that A1 is less than A2. The amplitude A1 is smaller than the amplitude of A2. So that's how you do it using these equations of motion.
Sorry, I might be forgetting something, but wasn't the motion equation for this omega t, or am I misremembering?
It is omega t.
Oh no, d. I remember there being a capital D somewhere in there. I think it was like for
Oh, that's just
displacement.
the amplitude. It's just this amplitude. You can have D or you can have A. So whichever you want to represent using that amplitude is fine.
Okay, cool. Thank you.
Okay. All right, let's take a look at another question. We're still here, we're talking about this question. We're looking at a spring oscillating up and down, up and down. So how do we make the spring oscillate up and down? So we start with a equilibrium point where you simply just hang it right here. You put a weight and it's stretched for a little distance, okay? And then at this point, you tap it and then it will start going up and down, up and down. So kind of like the horizontal spring, right? Again, you give it an initial velocity. Another way to make it go oscillate is at this equilibrium point where the mass is at rest, you drag it down even further, and then it's going to go up and down and up and down. All right, so we're given the mass of the block, and we know that when your mass is simply hanging there, it's stretched about 0.27 meters, and then you give it a velocity. The first question is, what is the spring constant of the spring? So this is really just kind of a calibration process. We need to know what kind of spring we're dealing with if we need to figure out what's going on with the oscillation. So this part is a simple application of the Hooke's law. We know at this point, the gravity has to match up with the spring force. These two forces has to be equal for the mass to be simply hanging there with a zero acceleration. So you can calculate the spring constant quickly by using the weight divided by how much it's being stretched, right? So you can get your K. And the next question is, okay, what is the oscillation frequency? Notice that is asking us about the F, right? How many hertz? So we need to do 2 pi over omega for my F. We need to use 2 pi divided by omega, the angular frequency. And what is our omega? The omega for a simple harmonic oscillation for a spring is square root of K over M. So you already got your K, right? You divide by M, you can get your omega, and you can get your frequency F. So all of that follows from the definition of these quantities. Now let's take a look at this question. This is interesting because so far we've been assuming it will just be following a simple harmonic motion type of motion. It will be a sine or cosine function. We just assumed that, right? But you see that we never really solved it for a vertical spring. We solved it for the horizontal spring, but what about the vertical spring? Do you think it will still give us exactly like an A cosine omega t kind of function, just like the horizontal spring? Or would it be different? Because in this case, you have also gravity, not just the spring force. Maybe that will change your equations of motion, right? So let's just get an idea of, okay, so maybe we have been in too much of a haste in getting, trying to solve this equation. Maybe we should slow down and find our equations of motion first for the vertical spring. So what do you think? Which one of these makes sense to you? It doesn't, you don't have, it could just be your intuition at this point. Okay. All right, so at this point, it would just be a prediction. It doesn't have to be correct. So whichever you think is reasonable, please put in your votes for this. Okay, all right, we will go for 10 more seconds. If you haven't put in your answer, please do so. All right, so let me go ahead and stop. We'll take a look at this together. All right, so we pretty much split between A and B, with B slightly more, which is reasonable right now. Right now we have two forces acting on the mass. When we are writing down equations of motion, what do we use? We used Newton's second law, right? So here, Newton's second law would be different because the forces are different. You have one more force. So would that change our answer? Let's take a look at this together to see if we can derive such an equation for this new type of oscillation. Okay, so we have these two states written right here. One is here is the spring is relaxed. So the first graph when spring is relaxed. Second picture moment is simply the mass is simply hanging in there. And the other one, let's look at another arbitrary moment when they start oscillating a random point during the oscillation. So let's draw the last one. So I'm gonna put my mass here. All right. And also let's set up our coordinates with 0 point here. And let's say, okay, we want upward to be positive. Okay, so at this point, you can see that the spring is stretched for how much? So you can see, okay, this total stretch is delta y. So here delta y is considered a known quantity. Okay, even though y is a variable, delta y is a known quantity. Something is already given. Okay, so here at this point you can see if this entire thing is delta y, and the location of my mass right now is at location of y, which is a variable. Okay, now the stretch will be delta y minus y. Okay, so that's how much the spring is being stretched at that arbitrary moment. Okay, so now we're ready to apply Newton's second law. So let's do that. We do F equals ma, just as we did before. And let's look at how many forces we have involved at this moment. We have the spring force pointing upward, so that's a positive. So spring force is K times the stretch. Okay, and we have gravity pointing down, so minus gravity, and that is equal to ma. Okay, so K delta y minus Ky minus mg is equal to ma. And what else do we notice? We notice that mg is equal to K delta y because that is the mass hanging in there, right? That is how much the spring is stretched depending on how much weight you put in. So mg equals K delta y. You can see that these two cancels out, giving us an expression that's negative Ky is equal to ma. Now acceleration is the second derivative of your position. So here we got a differential equation that looks like this. We get m dy dt, second derivative, is equal to negative Ky. Now this is exactly the same as what we got before for a horizontal spring. And the results, the solution to that is also the same as before. So very magically, for a vertical spring, we get the exact same equations of motion as we had before. And what about gravity? Why didn't gravity affect the result? So we're able to make gravity disappear because we have picked the equilibrium point, the new equilibrium point for the vertical spring is at this location. So this is your equilibrium point right here. Okay, so you're going up and down relative to that point. Instead of picking the relaxed point as your equilibrium. For our horizontal spring, when spring is totally relaxed, that's our equilibrium. We're going up and down relative to that point. But the vertical spring, because of the gravity, the equilibrium point is not when the spring is completely relaxed here, but it is at this point when the mass was just hanging there. Okay, so if we pick our correct equilibrium point, we're able to get rid of the influence of the gravity. So now the oscillation appears to be a pure sinusoidal function, up and down, relative to your new equilibrium point. So the answer is yes, we can use the same equation as long as we're specifying this equation is measured relative to this equilibrium point, which was different from what we had for the horizontal spring. So that part I want you to be clear about. So now we got that out of the way. We know that even for a vertical spring, we can still use the same equation to describe the position of the object. Very good. Now we're ready to use it to solve more, answer more of these questions. So for example, one of the questions could be, okay, after this many seconds, so let's say this is t equals 0. You give it a velocity and it starts oscillating. At this much second later, what is the speed of the block? Okay, so we know that, well, if we have an equation describing how velocity changing with respect to time, then we can find the velocity at any given time, right? We just need to plug in different t. Okay, so to get velocity, we need to get our new equations of motion. We need to make our equation satisfy the initial conditions. So at t equals 0, okay, remember y is 0. Okay, so because we have set our y is here, saying that this is our equilibrium, we are oscillating relative to this point. So that is very important. This has to be your 0 y position. You cannot set here is 0 because that's not our equilibrium point. Okay, so when t equals 0, your position is 0, you need a sine function. Okay, and also you are moving downward. If you had defined upward to be your positive, moving downward, we need to add a negative sign to your y because at after t is larger than 0, at time passing by, your position would have been under where you started. So you need to have a negative position because you're giving a velocity downward. You're moving down, right? So those are all our initial conditions. So from those initial conditions, you can write down this equation right away. And then take the derivative and you get your velocity is negative omega a cosine omega t because the derivative sign is a cosine, right? And the negative sign follows. All right. So looking at this equation, do we know everything we need? We know omega, right? We were given the time, we can plug in time. One thing we don't know yet is our amplitude. So we need to find our amplitude first. And again, this is a conservation of energy approach. Given this much velocity and so you have this much kinetic energy, how far could you go? How much could you stretch the spring? And you can calculate your A, and you can plug in everything in here to find the velocity at any given moment. So, so that is this particular question. You can see all of this we have already done in previous questions. So this last little bit is new. Usually some of these questions, they come together, right? the first order of question would be to figure out amplitude, or vice versa, given the amplitude, figure out your maximum velocity, and then figuring out at any given moment, what is your velocity, or they can ask you, what is your position, or they can ask you, what is your acceleration. No matter what they ask, you have your equation to describe these quantities, so you can calculate whatever question that they ask: position, velocity, or acceleration. So this is simple harmonic oscillation for a spring. The simple harmonic oscillation model, as I said, is very versatile. It applies to a variety of different things. So another thing that follows a simple harmonic oscillation model is a pendulum. You can have a simple pendulum where you really just have a string, and you have an object attached to a spring, and then let it go back and forth, right? So like a pendulum, or you can have like a stick pendulum, a stick, and that could go back and forth and back and forth. This is more like this is a physical pendulum, versus if you have just a string, that's a simple pendulum. Okay, so now we're going to shift gears to talk about pendulum, which is another kind of motion that follows simple harmonic oscillation model. So we want, at first step, is to show that is indeed following such a model. So we are going to derive, again, the equations of motion. So let's take a step back, thinking about, okay, how did we derive the equations of motion for the spring? That's what we did. We say, okay, equations of motion. All right, equations of motion. We want to find out the position of this object as a function of time. So the position is measured along this direction as x from the 0 point. So how does x change as a function of time? So this is our equations of motion for a spring. Now we have a pendulum. Okay, so for a pendulum, so this is, we start out with a stick pendulum going back and forth, and the position right now, you can see it's an angular position, right? Because this is a rotational motion. So it looks like, okay, which quantity describe angular position? It would be the angle, right? So the angle changes from smaller to bigger, up and down, up and down. So here, the position versus time equation would be a function for theta. How does theta change with respect to time? This is our goal. And think about what we did here. Here we used F equals ma to derive how x changed with respect to t. And we had a second order differential equation for our position. Here, since it's rotation, we need to use Newton's second law for rotation. So what is Newton's second law for rotation? Force become torque, mass become rotational inertia, and A becomes alpha, right? So that's why we start with torque is equal to I alpha for a pendulum, because this is our Newton's second law right now for rotation. And bear our goal in mind, we wanted to define a relationship between theta and t. Okay, so let's work this out one by one. First, let's find out what is our torque. Okay, so the torque, well, there is some weight of the stick, right? So there's our gravity. That is a force that provides such a torque. So I'm going to draw my force on the stick. And where would I draw this force? So if it is a uniform stick, I would draw it in the middle, because for any object, if it's uniform, its center of mass is always in the middle, right? So this is the halfway between, half middle point is the center of the mass for the stick. And that's where the gravity is acting upon. So that's my mg. Okay, so to get torque, what do I need? I need torque is R cross F. So you need the force and the level arm that is perpendicular to my force. So let me look at this. My level arm in this case is this red arrow right here. So that distance is R, okay, R radius times sine theta. So I have mg times r sine theta as my torque. And you can see it's trying to rotate it in a clockwise rotation direction. So that's a negative torque. All right. Now we are going to do a small angle approximation. So assuming your angle is small enough, it's not like you have taken it all the way up and let it go down. So if angle is small enough, sine theta is approximately equal to theta. Okay. Now you wonder, okay, why do you want to make sine theta equal to theta? Because as we said earlier, our goal is to define equation that describe the angle. So we want angle to come out. We don't want the sine of angle. Okay, so at small angles, theta is approximately sine theta. So I'm going to switch sine theta to theta. And I simply, let's leave I as a constant here. Your angular acceleration is the second order derivative with respect to time for theta. So there you go. We have an equation, second order differential equation for our angle theta. Okay, so these two are equal. You can see you can just rearrange it a little bit, moving all the constants to one side. So this is the second order differential equation you have, which looks exactly the same as our spring previously. So if you recall, what does our spring looks like, right? So it is d position dt second order is equal to negative of some constant times the position. And here is exactly the same. Okay, so d position dt second order is some negative constant times the position. So you know that you already know what kind of answer solution you're looking for. You can see this is the same as before. I get another sine pseudo function for this type of motion. Because you have a lot of constants, we put all our constants together and we use omega to represent these constants. So you can see now our angular frequency omega for a pendulum is square root of mass times g times the radius divided by I. So that is our physical pendulum. To make that into a simple case, a simple pendulum is as if all of your mass are concentrated at the bottom. So you can switch out the stick using a string. So the string has no mass and all the mass are concentrated at one end. So that is your simple pendulum. For a simple pendulum, you can verify this relationship by plugging the correct I and R. So for simple pendulum, you can see the center of mass is where the ball is, right? So this radius is simply L. And rotational inertia for a point particle is simply ml squared. Okay, so that becomes square root of g over L. Does that result, does that remind you of something you did at the beginning of the semester? Does that look familiar or does that ring?
Yeah, when we were going over units, we did this activity, like, but just instead of with like G and L, with like actually like length or meters and meters per second squared and stuff.
That's very good. I'm glad that you remember that. We had to write this relationship purely using dimensional analysis. So that was an example showing the how powerful dimensional analysis is. That is sort of a lot of times is what physicists do. When they want to get a relationship, they will assume certain quantities that may affect the result. For example, if you want to find out a period of the pendulum, So you're thinking, okay, I wonder what could matter. I think maybe the mass would matter. Maybe the length of the string I use could matter. And I'm doing this on Earth, maybe little g would matter, right? So you assume all of this variable would matter, and you just play with their power to make sure that the units add up. So if you need a relationship between time and g and L and mass, so assume they all have corresponding power to see what the power needs to be in order for the units to match up. Okay, so here the time had units of seconds, and nowhere does the kilograms come out. So you know that mass eventually disappear from the equation, and it has to be proportional to time would be L over G. So that was the time. Here is omega. No, time is 2 pi over omega. Okay, so you can see this agreed with our results from the beginning of the class. So omega for a simple pendulum is the square root of G over L. Let's take a look at this question. So we have a clock, right? The bottom of this clock is simply a simple pendulum where all of its mass are concentrated at the end. You adjust the clock by moving the screw up or down. So in this case, if the clock is running too fast, do you need to move that weight up or down? So here we're using the simple pendulum result that the angular frequency is G over L. Okay, and which means time would be 2 pi over omega, which would be 2 pi L over G. Okay, so if it is running too fast, how should we adjust the screw? You guys have already done this, so what are your thoughts?
So if it's running too fast, we need to make the period smaller. I mean longer. Sorry.
Longer, yes. So right now it's the period is too small. Yes, so we want to increase t.
Yeah. So then, so 2 pi is a constant, as is g. So the only way to increase t would be to increase L.
Yeah, so we need to increase L. Very good. So how do we increase L? We're moving the screw up or down.
And in order to do that, to make the pendulum longer, we move it up, so down.
Yes, very good.
Yeah.
To make it longer, we need to move it down. So it has a longer L and longer period. Very good. That's really just a direct application of this equation for a simple pendulum. So let's look at sort of the equivalent relationship between a stick pendulum versus a simple pendulum. For a stick pendulum to have the same period as a simple pendulum, then you need to use a simple pendulum that is a little bit shorter than the stick pendulum. So let's see. For a stick pendulum, all the center of the mass are concentrated at the middle point, at the center. So our radius would be L over 2 for a stick pendulum. And for rotational inertia is 1/3 ml squared. So I'm not sure if you still remember the results from before, because right now the rotation is happening toward one end. So for our stick, the rotational inertia relative to the center of the mass, if it's rotating relative to the middle point, that was 1/12 ml squared, right? So that is always something we can look up, or it will be provided at the question if there's a question. But now I'm not rotating toward the center, I'm rotating relative to the end, because this is the end is where I mount the stick pendulum, is going like this. So if you have a new axis, the new rotational inertia is the rotational inertia relative to the center plus the parallel axis theorem, saying that you can use m distance between these two axes squared. So this is we learned in the previous content parallel acts theorem. Okay. So the new I is the original I plus m times L over 2 squared, because the distance between these two axes are L over 2, half of the length of the stick. So that becomes 1 over 3 ml squared. So that's why we need to use 1 over 3 ml squared for our I. You can plug that in, you realize, well, that is equivalent to square root of g over 2/3 of L. So if you have a stick, or if you have a ball and a string, you use a ball that has the same mass as your stick and use a string that's 2/3 of the length as your stick. And now these two pendulums will be considered equivalent in the sense that they give you the same period, they give you the same oscillation time, back and forth, okay? So that's how, this is sort of a quick equivalent relationship between these two. Like if you see a stick pendulum, if you see something like this, you know right away that, okay, these two are equivalent in terms of the time, in terms of the oscillation frequency or the period. Okay, so that actually comes in handy to answer some more complicated questions. For example, this is a question you have already answered. This one is a little more complicated, but we can either do this by plugging the equations and do everything like that, or we can even answer this qualitatively. And that's enough for answering which one, to compare them, which one has a longest period, right? Okay, so we have case 1 and 2. We can see case 1 is just a stick pendulum. Case 2 is a little bit weird. It has a stick pendulum, but with a mass mounted in the middle, so added a mass. So if you want to compare the period between these two, how do we do it? All right, so let's take a look. So what does case 2 has a little mass in it. So that mass is as if you have a simple pendulum with M here and with a string that is half of L distance from your rotational pivot point. And case 1 is just a stick pendulum, right? Now these two are easy to compare. We know that a stick pendulum is equivalent to a simple pendulum that's 2/3 of the L. But now you use a simple pendulum that is 1/2 of the L, right? So obviously this one has a bigger denominator than this one. So omega 1 would be smaller than omega 2, okay? Because 2/3 of L is larger than 1/3 of the L. So omega 1 is bigger. Smaller. If omega 1 is smaller, then period is 2 pi over omega 1 would be larger than 2 pi over omega 2. So T1 is larger than T2, okay? So a stick pendulum is larger than a simple pendulum with half of the length. So this is something we know. And why do we do this? Because, well, the case 2 in the original question is a superposition of a stick versus a simple pendulum. They simply added together, right? It's sort of a morph of these two. Now I know that right now, period 1 is larger than period 2. So if you morph them together, you know, combine these two together to form a new pendulum, then the new period would make sense for it to be in between, right? So the new one should be in between T1 and T2, somewhere in the middle. So the period of the new pendulum, T new, will be in between T1 and T2. Okay, all right. So in this case, your new pendulum is your case 2, and your stick pendulum was your case 1. So here you got a relationship for the original question that was, this is your T1, this is your T2, this is your T new, and T1 has the longest period. So here we sort of worked it out without too much math. We kind of talked about it qualitatively by this relationship, knowing exactly how a stick pendulum switch to a simple pendulum. So we used this relationship. We can work it out in more detail with the math. So we can calculate the exact period for case 1 and case 2. And we will do that next time. So I won't see you guys on Friday because we have our Thanksgiving break. So I will see you on Monday. We'll try to finish our simple harmonic oscillation discussion, and we'll begin the fluid discussion. And we'll be able to finish all the fluid discussion next week with our 3 classes.
Are we gonna have a final review?
Sorry?
Are we gonna have a review for finals with you, or is
There
that
will
on
not
our?
be review. You will have to do your review by yourself using a practice exam as one of the resources you can use. And I strongly encourage to try to do more practice. You can review our examples we did in class, homework questions, and find some practice questions from the book when you prepare for the final. Okay. All right. I wish you guys a happy Thanksgiving holiday. Get some rest and recharge, and we will see you guys next week.
Bye,
Bye-bye.
Professor. Thank you. Have a great Thanksgiving.
Thank you.
Thanksgiving, Professor.
Thank you, you guys too.
Actually, I did want to ask,
Yeah.
For this final, will we still have the opportunity to upload our work for like partial credit points?
Yes, absolutely.
Okay. Thank you. Have a good Thanksgiving.
Thank you, you too.